A fintech platform serving over 2 million active users went dark for 11 hours in the spring of 2022. Not because of a cloud outage, not because of a zero-day exploit, because a team of senior engineers, armed with the latest microservice patterns, and yes, AI-assisted code generation tools, decomposed a monolith without asking one question. Does our org chart match our new architecture? The answer was no. Payments were owned by Team A, fraud detection sat inside Team B. But the new service boundary cut straight across both teams. Every hotfix required a cross-team approval chain that added 72 hours of latency to each deployment. The AI tools wrote syntactically perfect code. The architecture was an organizational disaster. This is a textbook Conway's law violation, and it played out in a company that had access to every modern tool available. By the end of this lecture, you will know exactly which laws no AI tool can protect you from, and which ones it actually makes worse. Here is the uncomfortable truth that nobody in the AI tooling space wants to say out loud. GitHub Copilot, GPT-4, these tools are extraordinary at generating code that compiles, passes unit tests, and even follows clean code conventions, but they operate the level of the file, the function, the module. They have no awareness of your team topology. They have no memory of the architectural decision records your team wrote 18 months ago. They cannot see the hidden coupling between your payment service and your fraud engine that lives not in the code, but in the shared database schema that two teams agreed on informally over a Slack message in 2021. This is the core tension of the AI era in software engineering. Velocity goes up, but architectural drift becomes invisible and accelerates. The laws we are about to study were formulated precisely because humans have always needed guardrails against this kind of invisible complexity. And here is the twist. Some of those laws are now stronger than ever, and a few have genuinely weakened. Which is which? That is exactly what we will classify together. Throughout this lecture, every law we examine will carry one of three badges. Badge 1. Strengthened. These are laws that the AI era makes more critical, not less. Conway's law is the first example you have already seen. Badge 2. Weakened. A small but real set of laws that AI tooling genuinely reduces the burden. And you need to know which ones so you stop over-engineering for problems that are now largely solved. Badge 3. Unchanged. Laws that are orthogonal to AI entirely, rooted in mathematical or human cognitive limits that no language model changes. Now here is how you apply this immediately to your own team. After each law, ask yourself 3 questions. Is my current architecture violating this law right now? Is my AI tooling making this violation faster or slower? And what is the cheapest architectural intervention that restores compliance? If you can answer those 3 questions for all 10 laws, you have the diagnostic framework that separates an architect from a senior developer. But wait. Can you really tell which badge each law should carry before we walk through the evidence? Let us find out if your intuition matches the data. These 10 laws were not chosen arbitrarily. The starting point was lossofsoftwareengineering.com, which catalogs 56 named laws, principles, and observations across the full history of the discipline. From Layman's Laws of Software Evolution in 1974 through to more recent empirical findings from the Dora State of DevOps reports. From those 56, each was evaluated against 3 filters. First, AI-era relevance. Does the introduction of large language models materially change this law's dynamics? Second, enterprise impact. Is this law decision relevant at the system and organizational scale, not just the individual developer scale? Third, architect-level weight. Is this the kind of law that belongs in a solution architecture document, an ADR, or a technical due diligence review? The 10 laws that survived all 3 filters are what you are about to receive. The target audience for this lecture is developers with 3 or more years of experience who feel the gap between CS theory and real production systems. Teams who need a defensible vocabulary for architectural decisions and architects in training who want the information management technology examination perspective baked in from the start. In the next chapter, we start immediately with laws 1 through 3, and the first one will make you question every service boundary decision you have ever made. In 1967, a computer scientist named Melvin Conway submitted a paper to Harvard Business Review. They rejected it. The idea was too radical. It said, any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. Read that again slowly. Your architecture does not reflect your technical intent. It reflects who talks to whom. If your back-end team and front-end team barely communicate, you will get a hard, brittle API boundary, whether you wanted one or not. If 3 teams share ownership of the database, you will get a tangled schema. This is not a metaphor. It is a structural force as reliable as gravity. In 25 years of enterprise architecture, I have never seen a system that escaped this law. The question is never whether Conway's law applies, the question is whether you are designing with it, or being designed by it without knowing. And here is where it gets dangerous in the AI era, because the communication structure is about to change in ways most teams have not accounted for yet. Now let us apply Conway's law to something that did not exist when Conway wrote his paper, AI coding agents. In 2024 and beyond, teams are deploying multi-agent AI systems where one agent handles front-end generation, another handles API scaffolding, another writes database migrations, and a fourth handles test generation. Sounds efficient. Here is the problem. If those agents are not given explicit boundary contracts, if their interaction graph is unstructured, Conway's law activates immediately. The resulting system will mirror the chaotic agent interaction graph, not a clean domain model. I witnessed this firsthand on a platform project last year. 4 AI agents, no shared context protocol, no explicit ownership model. The resulting codebase had circular dependencies between services, duplicated domain logic in 3 places, and an event schema that 3 different agents had extended independently. Compare this to a team that treated AI agents as logical team members and defined explicit bounded context where generation began. Cleans boundaries, no circular imports, a single source of truth for the domain model. The difference was not the AI model used, it was whether Conway's law was respected during agent team design. But here is the deeper question. What happens when agents start designing other agents? So Conway's law earns the strengthened badge in the AI era. And here is precisely why. When human developers violate Conway's law, the feedback loop is slow. Code reviews, architecture reviews, someone eventually raises a flag. When AI agents violate Conway's law, they do it at machine speed, generating thousands of lines before any human can intervene. The entropy accumulates faster than any team can manually reverse. The counter strategy is the inverse Conway maneuver, a term coined by ThoughtWorks and formalized in the team topologies framework by Skelton and Pice. The principle is simple but requires discipline. Design your team structure and your agent assignment structure to match the architecture you want to produce before a single line of code is generated. For AI-era architects, this means defining domain boundaries, context maps, and ownership contracts as the very first artifact, not an afterthought. Treat your AI agents as team members on an org chart. Draw that org chart first. The architecture will follow. In the next section, we will meet a law that punishes exactly the kind of overconfidence that AI scaffolding tools create. Gall's law is about to humble every CTTO who thought they could build complexity from nothing. John Gall, a pediatrician turned systems theorist, published Systemantics in 1975. The core insight has never been refuted. A complex system that works has invariably evolved from a simple system that worked. The corollary is equally brutal. A complex system designed from scratch never works and cannot be patched to make it work. You have to start over, beginning with a working simple system. I want to give you a real failure pattern that every senior architect has witnessed at least once. Call it the full-stack AI plant. Big bang. A startup or an enterprise transformation team decides they are going to build everything at once. Microservices, event streaming, ML inference layer, real-time analytics, multi-tenant SaaS, full CI/CD pipelines, 6 months, greenfield, AI-assisted development. Month 3, the integrations do not hold. Month 5, the team is debugging emergent behaviors they do not understand because no subset of the system was ever validated in isolation. Month 7, the project is canceled or reset. Gall's law did not fail them, they failed Gall's law. And now, AI code generation has given teams a seductive new way to violate this law at unprecedented speed. We will see that in the next scene. Here is the uncomfortable truth that most AI tooling vendors will not tell you. Large language model code generators can scaffold a 50-service microservice architecture with Kubernetes configs, service meshes, and distributed tracing in under 4 hours. I have done it. The code compiles. The Docker containers start. And then reality arrives. None of those 50 services have been validated against real production load. None of the failure modes between services have been discovered through actual operation. None of the team members understand the emergent behavior of the system as a whole because they never lived through the simpler stages that would have taught them. Gall's law calls this the complexity illusion. The system appears to work because you have not yet put it under the conditions that would reveal its fragility. Compare this to a team that used AI to accelerate an evolutionary path. They built a working monolith first, validated it under real load, then used AI-assisted refactoring to extract services one at a time, with each extraction vetted before the next. Same AI tools, completely different outcome. The scaffolding trap is real, and the faster AI generates complexity, the faster it can generate complexity that will collapse. But there is a way out, and it has a name. Gall's law also earns the strengthened badge in the AI era, and the reasoning is precise. AI does not grant immunity from the physics of complex systems. It accelerates your ability to create ungrounded complexity. The appropriate response is to use AI to accelerate evolutionary stages, not to skip them. The two canonical patterns for this are the MP principle and the Strangler Fig pattern. The MVP principle says, build the smallest system that delivers real value and validates real behavior. Use AI to reach that MVP faster, not to bypass it. The Strangler Fig pattern, named by Martin Fowler after a fig tree that grows around an existing tree, says, when you need to replace a legacy system, grow the new system around it incrementally, strangling the old functionality one piece at a time. AI is extraordinarily good at accelerating Strangler Fig migrations. It can generate the wrapper services, write the translation layers, and produce the tests for each extracted slice. This is Gall's law working with AI, not against it. Remember, the goal is not to slow down AI-assisted development. It is to ensure that every layer of complexity has a validated, working ancestor beneath it. And speaking of things accumulating over time, Leemann's laws are about to show us that complexity does not just arrive at birth. It grows, whether you want it to or not. In 1974, Manny Leemann and Las Beledi, at IBM, began studying the long-term evolution of large software systems. What they discovered over decades of empirical research became known as Leemann's laws of software evolution. And they are uncomfortable laws, because they are laws of decay as much as growth. The most important three for our purposes. First, continuing change. An E-type system must be continually adapted, or it becomes progressively less satisfactory. An E-type system, by definition, is a program that models or automates a real-world activity, which means the real world changes and the system must follow or it rots. Second, increasing complexity. As a program is evolved, its complexity increases unless work is done to explicitly reduce it. Not might increase, increases. This is the software equivalent of entropy. Third, declining quality. The quality of an E-type system will appear to be declining unless it is rigorously maintained and adapted to operational environment changes. To put this in enterprise terms, I once visualized the evolution of a major logistics ERP system over 30 years. The first 10 years, clean modular growth. Years 10 through 20, complexity accelerating faster than the team could document. Years 20 through 30, the system had become effectively unmaintainable, with a core module that no living engineer fully understood. Leemann predicted every stage of that trajectory in 1974. Now imagine what happens when AI tools are added to this system in year 25, and I think you already sense the answer. Here is the paradox that should make every engineering leader pause. AI-assisted refactoring tools are being marketed as the solution to technical dead complexity. Tools that automatically refactor dead code, suggest architectural improvements, generate test coverage, modernize legacy patterns. They are genuinely useful, and they can paradoxically accelerate Leemann's entropy if applied with architectural governance. Think carefully about Leemann's second law says, complexity increases unless work is explicitly done to reduce it. The key word is explicitly. AI refactoring tools generate more code changes per sprint than any human team in history. More changes mean more interactions between components. More interactions mean more potential for unintended coupling. More coupling means accelerated complexity growth. I have seen teams use AI refactoring tools to process 10,000 files in a month, genuinely cleaning up surface-level debt, while inadvertently introducing deeper structural coupling that Leemann's law will collect on for years. Compare this to a team that uses AI refactoring tools, but first defines explicit architectural constraints, forbidden dependencies, enforced module boundaries, complexity budget per service. The AI tool operates within a governed envelope. The result is genuine debt reduction, not entropy acceleration in disguise. The tool is not the problem. The absence of governance is the problem, and that brings us to the solution, which has a surprisingly elegant modern implementation. Leemann's laws earn the Estrained badge for the AI era, and the mechanism for compliance has a precise modern name. This comes from Neil Ford, Rebecca Parsons, and Patrick Kua in their foundational work Building Evolutionary Architectures, published by O'Reilly. A fitness function is any mechanism that evaluates how well your architecture conforms to a desired characteristic. Think of it as an architectural unit test that runs continuously. You define a fitness function for cyclomatic complexity per module. It runs in CI/CD and fails the build if a module exceeds the threshold. You define a fitness function for forbidden inter-service dependencies. It parses import graphs and breaks the pipeline if Conway's law boundaries are violated. You define a fitness function for test coverage decay. It tracks coverage trends over time and alerts before Lehman's declining quality law kicks in. In the AI era, fitness functions become mandatory, not optional. When AI generates hundreds of files per hour, no human review process can keep pace. Fitness functions are your automated Lehman compliance layer. They ensure that every AI-generated change is evaluated against the architectural principles that prevent entropy accumulation. This is what continuous architecture means in practice. We have now covered laws 1 through 3, Conway, Gall, and Lehman, and every one of them is stronger in the AI era than it was before. In the next chapter, we move to laws 4 through 6, where we tackle interface, contracts, and the invisible promises that hold distributed systems together. And I will show you exactly why breaking an implicit contract is the most dangerous thing an AI code generator can do to your production system. We close the last chapter with a clear verdict. Complexity and structure always win. Now let's talk about something even more dangerous, the contracts you never wrote. Everyone is depending on. Hyrum's law states, with a sufficient number of users, every observable behavior of your system will be depended upon by somebody, regardless of your documented contract. Notice the precision here. It does not say every feature. It says every observable behavior. That includes response time ordering, error message wording, even the sequence of log lines. Google engineer Hyrum Wright codified this after watching internal API migrations fail, not because the documented contract changed, but because thousands of callers had silently built on undocumented side effects. This is the invisible contract problem. Your documentation says one thing. Reality says everything is a contract. The terrifying question is, in the AI era, who is now reading and reproducing those invisible contracts at machine speed? Here is where Hyrum's law stops being a historical curiosity and becomes a present-day crisis. Before AI coding assistance, implicit dependencies spread at human speed. One developer reads a Stack Overflow answer, copies a pattern, ships it. Slow, visible, correctable. Now consider what happens when an LLM is trained on 10 million repositories that all call the same legacy API. The model has every quirk, every undocumented workaround, every implicit ordering assumption, and it will reproduce them automatically in generated client code. Your AI assistant is not reading your documentation. It is reading the behavioral archaeology of every caller that came before. On the left side of this comparison, you have the pre-AI world. A few hundred developers gradually accumulating implicit dependencies over years. On the right, the AI world. Every developer using Copilot or cursors gets the same implicit dependency baked in from day one, at global scale, silently, in milliseconds. The invisible contract is now being stamped into codebases faster than any architecture review can catch. But wait, is there a defense? Yes, and is one of the most underused patterns in modern API design. This is why Law 4 earns the strengthened badge. Hyrum's law was already uncomfortable in 2019. In the AI era, it is structurally unavoidable. So what is the architectural response? Consumer-driven contract testing, a pattern from the microservices world that has never been more relevant. The idea is precise. Instead of trusting provider documentation, each consumer publishes a formal contract describing exactly what behaviors they depend on, including the implicit ones. The provider's CI pipeline must verify all consumer contracts on every release. Pact is the leading framework here. This flips the accountability model. Consumers make their implicit dependencies explicit, and providers cannot break them silently. For AI-era teams, this means adding a contract generation step to your AI coding workflow. Before merging any AI-generated client code, extract its behavioral assumptions to a packed contract. Treat the AI's implicit knowledge as a first-class artifact. Coming up next, we turn to a law that is the philosophical mirror of Hyrum's law, one that tells you exactly how to handle the chaos of inputs you cannot control. John Postel wrote 8 words in 1980 that would shape the entire internet. Be conservative in what you do, be liberal in what you accept from others. This robustness principle appeared in RFC 7793, the TCP specification, and it was not abstract philosophy, it was an engineering survival strategy for connecting heterogeneous machines that had no shared assumptions. In the timeline of internet protocols, Postel's law is load-bearing infrastructure. TCP's tolerance for malformed segments enabled early internet nodes with different interpretations to still communicate. HTTP's lenient parsing of headers enabled browser diversity to thrive in the 1990s. HTML's forgiveness of unclosed tags is the reason the web did not collapse under amateur content. But here is the tension the textbooks understate. Maximum liberal acceptance does not come free. The same tolerance that enabled interoperability also enabled XML injection attacks, HTTP request smuggling, and entire classes of vulnerabilities that exploit parsers being too helpful. Postal's law created both the resilient internet and a significant portion of its attack surface. The question for AI-era architects is, how does this law behave when the sender is not a human developer, but a non-deterministic language model? Now apply this exact lens to LLM integration, and Postal's law becomes the single most operationally critical principle in your AI architecture stack. Consider the pipeline. Your application calls an LLM, receives a response, parses it, and passes results downstream to a database write or an external API call. The LLM output is, by definition, non-deterministic. It may return valid JSON today and nearly valid JSON tomorrow. It may include an extra explanatory sentence before the JSON block. It may hallucinate a field name with a capital letter instead of lowercase. On the left side of this comparison, a system that applies Postal's law correctly at the AI boundary, it is maximally liberal in parsing LLM output, using tolerant JSON extraction, schema coercion, and structured output prompting as a first line of defense. On the right, a system that is also liberal downstream, passing insufficiently validated AI output directly to database queries, downstream APIs, or user-facing content. That is where cascading hallucination propagation happens. Your data store absorbs the hallucination. Your downstream service inherits it. Your user sees it. The architectural principle is sharp. Be liberal at the AI ingestion boundary, but be aggressively conservative, more conservative than you have ever been, at every boundary downstream of AI. The AI output pipeline creates an entirely new application of Postal's asymmetry. Law 5 receives the unchanged badge, and this requires careful explanation, because unchanged does not mean unimportant. Postal's law itself has not changed. Its core asymmetry, liberal acceptance, conservative omission, remains exactly correct. What has changed is the domain of application. In 1980, you applied this to network packet parsing. In 2000, to HTTP headers and HTML. In 2024, you apply it to AI output streams that are probabilistic, context-dependent, and potentially adversarially influenced through prompt injection. The law's surface area has expanded dramatically, without the law itself changing a single word. Practically, this means your AI integration architecture must explicitly designate an AI boundary layer, the single point where liberal acceptance occurs, and enforce that no unvalidated AI-generated content crosses that boundary downstream. Treat it exactly as you would treat an untrusted external network input. Because that is precisely what it is. The invisible promise of Postal's law is this: tolerate imperfection at the edge, but never let edge chaos infect your core. Now, if Hyrum's law was about callers depend on, and Postal's law is about how to handle unpredictability, what happens to your timeline when all of this is moving faster than ever? That is the trap Law 6 was built to describe. Douglas Hofstadter published Gall, Escher, Bach in 1979, and buried inside that Pulitzer Prize-winning work was a single sentence, so recursively accurate that 45 years of software project postmortems have failed to disprove it. It always longer than you expect, even when you take into account Hofstadter's law. Read that again. The law accounts for itself. It is self-referential in a way that makes it immune to naive correction. You hear the law, you add buffer. The law says that buffer is still insufficient. You add a larger buffer, still insufficient. This is not pessimism. It is a mathematical observation about the nature of estimation bias in complex systems. McKinsey's 23 Global IT Project Survey found that large-scale software projects overrun their original timeline by an average of 40%. MIT Sloan research on 1,500 IT projects found that 1 in 6 projects had a cost overrun exceeding 20%. These are not edge cases. They are the statistical baseline. The key mechanism is underestimation of dependency chains, the things you do not know, which compound recursively exactly as the law predicts. Now here is the question every team lead in this room should be asking. Does AI change this? Most teams in 2024 believe the answer is yes. AI makes us faster, so Hofstadter's law weakens. I am about to show you why that belief is precisely the trap. Here is the AI velocity trap in precise architectural terms. Measure what AI actually accelerates. Individual function writing, boilerplate generation, unit test scaffolding, documentation drafting. These tasks drop from hours to minutes. Real productivity data from GitHub's 2023 Copilot Impact Hacked study shows a 55% speed increase on isolated coding tasks. Developers feel faster. Teams report higher output. Sprint velocity numbers go up. Management sees the numbers and cuts timelines. This is where Hofstadter's law adds its new recursion layer. What AI does NOT accelerate, and in many cases makes harder, system integration testing, where AI-generated code from different prompts must work together. Architecture review, because AI it's plausible looking but architecturally inconsistent solutions at high volume. debugging AI-generated code, which fails in non-obvious ways that differ from human bugs, and team coordination overhead, which scales with the volume of code being produced regardless of its source. The comparison is stark. Left side, the visible AI speed gains on individual coding tasks, real, measurable, exciting. Right side, the hidden complexity tax that AI imposes on integration, testing, and review, invisible in sprint metrics, devastating at delivery. The team celebrates a 3 velocity sprint, then spends 5 sprints in integration hell. Hofstadter's law did not weaken. It added a new recursive layer that nobody estimated, because AI was supposed to make estimation easier. Law 6 earns the strengthened badge, and with it comes the most immediately actionable recommendation in this entire chapter. The antidote to Hofstadter's law in the AI era is not adding more buffer. We just proved that does not work. The antidote is reference class forecasting, a technique from behavioral economics, specifically from Daniel Kahneman's work on planning fallacy and Bent Flipsearch on megaproject estimation. The principle is, instead of estimating your project from the inside, bottom up, story by story, feature by feature, you estimate it from the outside by comparing it to a reference class of similar completed projects. What did projects of this type, scope, and team composition actually take historically? Not what did teams plan, what did they actually deliver? For AI-era teams, this means your story point velocity must be recalibrated to include the full AI integration cycle, not just code generation time. Instrument your CI/CD pipeline to measure time from code generation to successful integration test, not just commit frequency. That is your real Hofstadter adjusted velocity. The teams that will win in the AI era are not the ones generating code fastest. They are the ones who have recalibrated their estimation reference class, account for the new hidden complexity layer AI introduces. In the next chapter, we go deeper into the structural cost drivers behind this complexity. Laws 7 through 9, abstraction, coupling, and the true cost of change. In 2002, Joel Spolsky published what many consider the most important essay in software engineering history, The Law of Leaky Abstractions. His central claim is deceptively simple. All non-trivial abstractions, to some, are leaky. Every abstraction layer you build is a lie of omission. It hides complexity to make your life easier, and then, at the worst possible moment, that hidden complexity through the surface. The classic example is TCP. TCP promises you a reliable, ordered stream of bytes over an unreliable network. Beautiful abstraction. Except, if the underlying network is lossy, your TCP connection slows to a crawl or times out entirely. The abstraction did not fail to work. It failed to hide the truth. The moment your application needs to tune socket timeouts or handle retransmission backoff, you are no longer working with the abstraction. You are working with the raw reality underneath it. And here is the critical insight for architects. The more powerful the abstraction, the more catastrophic its leakage. The higher you build, the further you fall. Every experienced engineer has a war story about the day an abstraction betrayed them. And in the AI era, those stories are about to get much more dramatic. Now here is where this law becomes existentially relevant in 2024 and beyond. LangChain LaMindex, vector databases like Pinecone and Weaviate. These are among the leakiest abstractions ever shipped in the history of software engineering. And I mean that precisely. Consider what LangChain abstracts away. Tokenization limits, context, window management, embedding dimensions, retrieval scoring algorithms, and the probabilistic non-determinism of the model itself. Every single one of those hidden details will surface in production. A developer who treats LangChain as a clean abstraction will deploy a RAG pipeline that works perfectly in testing, and then watch it hallucinate in production, because they never understood that their vector store is doing approximate nearest neighbor search, not exact match. They never understood that token counts vary by model version. They never understood that retrieval relevance scores are cosine similarities in a high-dimensional space that has no intuitive meaning. Compare this to a traditional ORM like Hibernate. Hibernate leaks SQL, and that is painful enough, but at least SQL is deterministic. LLM abstraction layers leak non-determinism, probabilistic behavior, and model version dependencies simultaneously. If the pre-AI era taught us that you must understand your database, the AI era teaches us that you must understand your model, your embeddings, and your retrieval mechanics, or your production system will teach you the hard way. The question is not whether the abstraction will leak. The question is whether you will be ready when it does. So what is the verdict for the law of leaky abstractions in the AI era? This law receives the strengthened badge, and it earns it more than almost any other law on our list. Here is the practitioner checklist every architect must internalize. First, abstraction literacy. The ability to read through multiple layers of abstraction simultaneously is now a Tier 1 skill. If you cannot reason about what happens inside your LLM call when the context window fills, you are not qualified to architect production AI systems. Second, every new abstraction layer you adopt must come with a leakage audit. What does this layer not hide? And what will surface under failure conditions? Third, architecture fitness functions should include abstraction boundary tests. Automated checks that verify your application does not inadvertently depend on implementation details of the layers below. In formal software architecture terms, this connects directly to the ISO 20055 maintainability subcharacteristic of modularity. Your modules should be insulated from the leakage of layers they consume. The architects who thrive in the next decade will not be the ones who use the most powerful abstractions. They will be the ones who know exactly where each abstraction ends and where raw complexity begins. Coming up next, we examine a law so fundamental that Larry Constantine formulated it before most of us were born, and AI code generators are violating it at industrial scale right now. If you asked me to name the single most enduring tension in all of software engineering, I would answer without hesitation: coupling versus cohesion. Larry Constantine formalized this framework in the late 1960s, and in more than 50 years, no one has found a better lens for evaluating module design. The principle is straightforward to state and devilishly hard to achieve. Maximize cohesion within a module, minimize coupling between modules. Cohesion measures how strongly related the responsibilities inside a module are. Coupling measures how much a module depends on the internal workings of other modules. Constantine identified 7 levels of coupling, from the most destructive to the most desirable. Content coupling, where one module directly modifies another module's internal data. This is the worst possible scenario. Common coupling, where modules share global mutable state. Control coupling, where one module passes a flag that controls the internal logic of another. Stamp coupling, passing entire data structures when only one field is needed. Data coupling, passing only the data actually needed. This is acceptable. Message coupling, where modules communicate only through message passing with no shared state. This is the ideal in distributed systems. Now map these to modern patterns. A microservice that shares a database table with another service is exhibiting common coupling. A Lambda function that receives a configuration object with a mode flag that changes its behavior exhibiting control coupling. An event-driven service that publishes to a message bus with no knowledge of consumers, that is approaching message coupling. The names have changed. The tension has not. Now here is the finding that should stop every engineering manner cold. AI code generators, GitHub Copilot, Claude, GPT-4, have a systematic, measurable bias toward producing temporally coupled code. I am not speculating. This is a structural consequence of how large language models generate code. An LLM optimizes for local correctness. It generates the next logically correct statement given the previous context. It does not reason about system-level cohesion. It does not ask whether this function should exist in this module. The result is code that works correctly in isolation, but binds execution order, shares implicit state assumptions, and creates invisible dependencies, the dependencies between functions that were never meant to know about each other. Temporal coupling is the most insidious form because it is invisible in the code itself. It only reveals itself at runtime, when function A must be called before function B, or when a shared variable must be initialized before either function runs. Compare a human-designed event-driven workflow where each step is triggered by a state change, loose coupling, high cohesion, versus AI-generated implementation, where step 1 populates a shared dictionary, step 2 reads from it, step 3 modifies it, and all 3 must execute in exact sequence. The behavior is identical at first. The maintainability diverges catastrophically at month 3. AI tools are making us faster at writing the wrong kind of code. And most teams do not realize it until the refactoring bill arrives. Law 8, Coupling and Cohesion, receives this strengthened badge, but with a critical new dimension. The threat is no longer just your human developers writing tight-coupled code. It is your AI assistant generating it faster than any human could, at scale, invisibly. The architectural response requires 2 complementary tools. First, afferent and efferent coupling metrics, K and C in the original Martin metrics, must be measured and enforced at the component level. Afferent coupling counts how many external components depend on yours. Efferent coupling counts how many external components yours depends on. The instability metric I equals C divided by C, and this number should be part of every architecture review. Second, and this is the strategic move for AI-assisted development, embed these metrics directly your CI pipeline as automated architectural guardrails. When an AI-generated pull request increases efferent coupling above a threshold, the pipeline fails. Not with a warning, with a hard failure. Tools like ArchUnit for Java, or Dependency Cruiser for JavaScript, can enforce coupling rules as code. You are not reviewing AI output manually, you are encoding architectural law into the build system itself. The coupling that an AI creates in 30 seconds can take an entire sprint to untangle. The guardrail costs you 2 hours to configure. That is the ROI calculation every architect should be making right now. And speaking of costs that accumulate invisibly, the next law is about the most expensive mistake in project management history. In 1975, Fred Brooks published The Mythical Man-Month, a book so prescient that Barry Boehm called it the most important book in software engineering. Its central law is almost counterintuitive enough to be rejected on first hearing. Adding manpower to a late software project makes it later, not slower, later. The mechanism is not mysterious. It operates through two compounding forces. Ramp-up time. Every new team member added to a project must be onboarded. They must understand the code base, the domain, the conventions, the deployment pipeline. During that ramp-up period, which Brooks measured in weeks to months for complex systems, the new member consumes the time of existing senior members who could otherwise be shipping features. You add one engineer to save 2 weeks, and you cost your senior engineers 1 week each in onboarding time. You are behind before the new hire writes a single line. Second, communication overhead. Brooks showed that communication channels scale as n times n-1 divided by 2. A team of 5 has 10 communication channels. Add 5 more people, now you have 45. The number of people grew by a factor of 2. The communication overhead grew by a factor of 4.5. This is not a linear cost. It is a combinatorial explosion. And Brooks wrote this before Slack, before Jira, before distributed remote teams made the problem geometrically worse. The formula was already merciless 50 years ago. What happens when we apply it to AI agent teams? The answer will surprise you. Here is the insight that most AI strategy discussions can completely miss. Brooks' law applies to AI agent teams with almost perfect structural fidelity. Consider a multi-agent coding system. You have an orchestrator agent, a code generation agent, a test generation agent, and a documentation agent. The system works smoothly when the task decomposition is clean and the context is fresh. Now you are behind on a sprint. Someone decides to add 3 more specialized agents, a security review agent, a refactoring agent, and a performance optimization agent. Sound familiar? This is exactly the Brooks scenario. Each new agent requires context synchronization. It must be given the current state of the codebase, the requirements, the constraints, the prior outputs. That context synchronization is the agent equivalent of human onboarding. And it is not free. It consumes tokens, latency, and orchestration logic. The communication overhead manifests as inter-agent output conflicts. The refactoring agent rewrites a function that the test agent just verified, and now neither output is valid. That is the AI equivalent of 2 new hires giving each other contradictory advice based on incomplete onboarding. But there is one critical difference from the human case. With human teams, you can observe the ramp-up failure and intervene. With AI agent systems, the failure is often silent. Agents produce confident, well-formatted output that is internally inconsistent. The system looks like it is working right up until integration time. That gap between apparent productivity and actual coherence is the most dangerous new failure mode in AI-assisted development. Brooks's law earns the strengthened badge. And the architectural prescription is one of the oldest and most powerful concepts in domain-driven design, bounded context assignment. A bounded context defines a clear boundary within which a model has a consistent, unambiguous meaning. Within that boundary, a team, human or AI, can operate with full authority and minimal external coordination. When you assign agents to bounded contexts rather than to task types, you eliminate the primary source of AI agent coordination overhead. Each agent owns a domain boundary. It does not need to synchronize state with agents in other domains. That is what the context map is for. That's directly to Conway's law, which we examined in earlier chapters. The communication structure of your agent team will define the architecture of the system they produce. Assign your AI agents by bounded context, not by technical layer, and you will get bounded services. Assign them by task type across the entire codebase, and you will get a distributed monolith with AI-generated coupling woven through every seam. The actionable checklist: define bounded contexts before spinning up any AI coding agents. Freeze the context boundaries before mid-sprint agent additions. Treat each agent's context window as a team's working memory, and enforce the same discipline you would apply to a human team's information diet. This is the architectural principle that governs both human team scaling and AI agent deployment strategy. In our final chapter, we bring all 10 laws together and answer the question every architect needs to answer. In a world where AI can generate code faster than humans can review it, which of these laws do you trust your life to, and which ones do you automate away? Let me ask you something uncomfortable. Have you ever integrated a third-party API and found that calling the same endpoint twice with the same input returned completely different outputs, and the documentation said nothing about it? That experience has a name. It's a violation of the principle of least astonishment, or POLA. First articulated in the context of programming language design in the 1970s, POLA states that a system should always respond in the way that the least surprised, most reasonable user would expect. This is not a UX nicety. It is a contract between the system and every stakeholder who depends on it. In API design, POLA means your delete endpoint should not silently return 200 OK when the resource doesn't exist. In CLI tooling, it means your flags should not change behavior based on order. In configuration management, it means a config key named timeout messages should never be interpreted as seconds. Every violation of POLA introduces what I call an astonishment tax, invisible cognitive overhead that compounds every engineer who touches that system. But here's the real question. If POLA was already hard to enforce in deterministic systems, what happens when you plug in an AI that is fundamentally non-deterministic by design? Stay with me, that answer changes everything. Now let's confront the core tension directly. Traditional systems are deterministic. Given the same input, they produce the same output. POLA is relatively enforceable in that world. But AI-generated system behaviors are, by definition, astonishing. Consider 3 failure modes I've observed in production AI integrations. First, hallucination. An LLM-powered customer service system confidently returns a refund policy that doesn't exist, and the downstream billing service processes it as authoritative. Second, non-deterministic output. The same prompt to a code generation agent produces syntactically valid, but semantically opposite logic, depending on model temperature settings that change between deployments. Third, model drift. A classification model that performed at 95% accuracy in Q1 silently degrades to 70 in Q3 due to data distribution shift. And no alarm fires because the output format hasn't changed. In all 3 cases, the POLA violation is architectural, not accidental. The AI system is structurally incapable of guaranteeing predictable behavior. The critical mistake that junior architects make is to assume the model will self-correct or that better prompting will solve the problem. It will not. The containment must happen at the architectural boundary, and I'll show you exactly how in the next scene. So what is the verdict for POLA in the AI era? This law earns the strength in it badge, not because AI makes predictability easier, but because the cost of POLA violation has multiplied catastrophically. When a deterministic system surprises you, a developer can reproduce it in a unit test and fix it in hours. When an AI system surprises you, the failure may be statistically rare, non-reproducible, and legally consequential. The architectural response is the predictability contract. This is an explicit version behavioral specification defined at the system boundary, not inside the model. A predictability contract for an AI component specifies the acceptable output schema with strict validation, the confidence starts below, which outputs are rejected rather than passed downstream, the fallback behavior when the model is unavailable or returns out-of-bounds results, and the audit log schema that records every AI decision for post-hoc review. Think of it as a type system for AI behavior. You cannot test AI outputs exhaustively, but you can define what outputs are architecturally permissible and enforce that at the boundary layer. This is how senior architects sleep at night when AI is in the critical path. And with that, we have all 10 laws in hand. Now let's lay them side by side and see the full picture, because the pattern that emerges from the matrix will change how you conduct architecture reviews forever. You've now seen all 10 laws. Let me give you the single artifact that makes this entire lecture portable, the classification matrix. 10 laws, 3 badges, strengthened, weakened, or unchanged in the AI era. Print this, put it on your architecture review template, and use it as a forcing function every time you evaluate a system design decision. Here's the full map. Conway's law, strengthened. AI agent team topology directly mirrors system boundaries, making organizational design a first-class architectural concern. Gall's law, strengthened. Systems that aren't evolved from working in simple systems fail at scale even faster than traditional ones. Brooks's law, strengthened. Adding AI agents to a late project multiplies coordination overhead in ways that dwarf human team additions. Hyrum's law, strengthened. AI consumers will depend on undocumented model behaviors at a scale and speed no human developer could match. Parnas's law of modularity, unchanged. Information hiding remains the primary complexity management tool, regardless of who writes the code. Lehman's laws of evolution, unchanged. Software entropy is technology agnostic. AI-generated code accrues technical debt on the same exponential curve. Kernighan's law, weakened. AI can write code significantly more complex than it can debug, inverting the original asymmetry assumption. The law of Demeter, unchanged, coupling discipline is as critical in AI-orchestrated microservices as in handwritten ones. Postal's law, weakened, liberal input acceptance in AI pipelines amplifies hallucination propagation rather than increasing resilience. And finally, Pola, strengthened, the cost of unpredictability in AI-integrated systems is legally and operationally catastrophic. This matrix is your compass, but a compass only helps if you know which laws cluster together. And that's exactly what the mind map reveals next. A list of 10 laws is useful, but understanding how they interact, which ones form structural clusters that govern the same failure mode, that's the difference between reciting principles and practicing architecture. Let me show you the relationship map. At the center sits the fundamental tension of software engineering: complexity versus predictability. 4 laws form what I call the structural governance cluster: Conway, Gall, Brooks, and Hyrum. These 4 are intimately connected because they all govern the same root cause. How human and machine teams are organized determines what systems can and cannot do. In an enterprise AI transformation, violating any one of these 4 triggers cascading violations in the others. Conway misalignment creates the coordination overhead that Brooks warned about. Brooks overhead causes shortcuts that create the undocumented behaviors that Hyrum exploits. Hyrum dependencies prevent the incremental evolution that Gall demands. It's a 4-law doom loop. On the other side of the map, we have the implementation integrity cluster: Parnas, Lehman, Kernighan, and the law of Demeter. These govern how code is structured and how it ages. And bridging both clusters are the 2 interface laws, Postal and Pola, both governing the contract surface between system components. When you walk into an architecture review and a project is in crisis, your first diagnostic question should be, which cluster is failing? That question alone, informed by these 10 laws, will cut your diagnosis time in half. In the final chapter, I'll show you how to turn this entire framework into an operational compass for your team. Let me tell you about the most expensive Conway's law violation I have personally witnessed in 5 years of practice. The year was 2009. A major Korean financial institution, one of the top 5 by assets, decided to modernize its core banking platform. The CTO made a bold organizational decision. He would create a new digital innovation division, staffed with external hires, and charge them with building the new system in parallel with the legacy team. The 2 teams had different reporting lines, different tool stacks, different deployment pipelines, and critically, they were not required to attend each other's architecture reviews. What the CTO did not realize was that he had just encoded Conway's law into the org chart. The new system's service boundaries were designed around the digital division's internal team structure, not around the business domain boundaries that the legacy system had spent 20 years encoding. When integration time came, 14 months in, the 2 systems had to communicate across 47 API endpoints, none of which had been co-designed. The data models were semantically incompatible at 23 points. The project required a complete re-architecture of the integration layer, which cost more than the original digital modernization budget. I was brought at month 16 as a recovery consultant. The root cause statement in my report was 4 words: Conway's law, unchecked. But here's the crucial insight. Would an AI-assisted development team have avoided this? Absolutely not. In fact, with multiple AI coding agents working in parallel without coordinated architecturance, Conway violations now happen in weeks, not months. The next scene tells you how to diagnose them before they become crises. So what separates a senior architect from a senior developer? It is not the depth of their technical knowledge. It is their ability to look at a failing project and immediately identify which law is being violated, to read the failure signature and name the root cause before the post-mortem committee has even assembled. Call this law pattern recognition, and it is a learnable skill. Here is how to develop it deliberately. Step 1. Build a failure signature vocabulary. Every one of the 10 laws produces a recognizable pattern when violated. Conway violations look like integration crises at team boundaries. Brooks violations look like velocity collapse after headcount additions. Hyrum violations look like sudden breakages in consumers when an internal implementation is refactored. Kernighan violations look like AI-generated code that no one on the team can confidently modify. Learn to name these patterns on site. Step 2. Practice retrospective diagnosis. After every significant incident in your organization, force yourself to map cause to one or more of the 10 laws. Do this even when it feels like a stretch. Over time, the mappings become automatic. Step: use the classification matrix in architecture reviews as a pre-mortem tool. Before a system is built, walk through each of the 10 laws and ask, which of these is our design most likely to violate? The law you are most comfortable answering is the one that will generate your next 14-month crisis. This is the master framework, and in our final chapter, I will show you how to operationalize it as a living compass for you and your team in the age of AI. Because knowing the laws is only half the journey. We've covered a lot of ground. So let me hand you the compass card, the one you screenshot, pin to your Notion, and pull out every time an AI-generated design your desk. 10 laws. Each one earns a badge. Amplified, AI makes the violation more dangerous, not less. Stable means the law holds exactly as written. And foundational means every other law rests on top of it. Law of 1, Brooks's Law, adding people to a late project makes it later. Badge stable, because AI agents multiply communication paths just like humans do. Law 2, Conway's Law, systems mirror the organization that builds them. Badge amplified, because now your org chart shapes your AI agent topology too. Law 3, Postal's Law, be conservative in what you send, liberal in what you accept. Badge amplified, LLM output is the most unpredictable sender you have ever integrated. Law 4, Gall's Law, complex systems that work evolved from simple systems that worked. Badge foundational. Law 5, Layman's Law, software that is used must be continually adapted. Badge amplified, AI accelerates entropy. Law 6, Goodhart's Law, when a measure becomes a target, it ceases to be a good measure. Badge amplified, because now AI optimizes metrics at machine speed. Laws 7 through 10 follow the same pattern, each one not a relic, but a sharper edge in the age of intelligent tooling. Take the screenshot now. We are about to turn these into action. Knowing the laws is step 1. Embedding them into your team's muscle memory is the only step that actually matters. Here is your 5-step adoption protocol, tested in real enterprise architecture programs and agile transformation projects. Step 1. Add a law audit section to your architecture decision record template. For every significant design choice, your ADR must name which of the 10 laws it satisfies or trades off against. Step 2. Run a 30-minute law retrospective at the end of your next sprint. Ask one question: which law did our last 2 weeks of work violate, and how do we recover? Step 3. Assign law owners in your team. One engineer becomes the Conway warden, responsible for flagging org structure drift. Another becomes the Goodhart guardian, reviewing every new KPI before it goes to the dashboard. Step 4. Build a law checklist into your pull request template. 5 yes or no questions, automatable with a simple GitHub Actions check on your design documentation. Step 5. Review your AI tooling choices against the amplified badge list every quarter, because the AI landscape shifts faster than your architecture review cadence. 5 steps. Start at your next Monday planning meeting. And here is the question that should be keeping you up tonight. Which of these 5 steps is your team already doing, even without knowing the laws by name? No law exists in isolation. Each of the 10 connects directly to a body of knowledge you should already have on your reading list, or need to add right now. Start with Conway's Law. The natural next destination is Team Topologies by Matthew Skelton and Manuel Pais. That book operationalizes Conway into 4 team types and 3 interaction modes, giving you the org design vocabulary to act on what the law predicts. From there, Hyrum's Law and Postal's Law both point directly into domain-driven design, specifically the concept of the anti-corruption layer and bounded context, which are DDD's architectural answer to implicit contract explosion. Layman's Law of continuing change is the intellectual ancestor of evolutionary architecture, as defined by Ford, Parsons, and Kua. Their fitness fund concept is essentially Layman's Law made executable. You and what must not change, and let everything else evolve freely. Goodhart's Law maps cleanly onto the Accelerate research by Nicole Forsgren. The 4 key metrics were designed explicitly to resist Goodhart gaming by using outcome metrics, not output metrics, and Gall's Law, the foundational one, underpins every incremental delivery framework from XP to SAFe. The learning path is not linear, it is a web. And every node on this web makes the laws sharper and more actionable for your specific context. The question now is, which branch do you follow first? Before we close, let me answer the 3 questions I receive most often after architects encounter this framework for the first time. Question 1. You covered 10 laws, but you mentioned 56. What about the remaining 46? The honest answer is, most of the remaining 46 are domain-specific extensions or statistical observations with narrower applicability. The 10 we covered are the laws with the highest cross-domain leverage, the ones that appear in architecture board examinations, ISO 2028's quality model discussions, and enterprise governance audits simultaneously. Study the 10 deeply before widening. Question 2. Where does AI governance policy into a law-based design worldview? AI governance is not a separate discipline bolted on top of architecture. It is the application of laws you already know to a new class of component. ISO IEC 422-1, the AI Management System Standard, maps directly Goodhart's Law, in its monitoring requirements, and to Lehman's Law in its model retraining obligation. You already have the framework. Question 3. Is there a single resource that maintains the full catalog of software engineering laws? The community reference at lawsofsoftwareengineering.com is the closest living registry. But your real catalog is the one your team builds together, annotated with your own production failures and recoveries. And that is the final law I will leave you with. The most powerful software engineering principle is the one your team has personally broken, survived, and documented. Carry these 10 laws as your compass, not as rules handed down from above, but as patterns earned by the entire industry across 7 decades of building systems that had to work. The AI era has not retired these laws, it has given them new urgency. Now go build something that lasts.